I want to start today with something that feels like a paradox, right at the heart of this whole AI boom.
Okay.
We have this big assumption that if you want a smarter computer, you feed it more data. You want it to write poems, give it all the poetry, you want it to code.
You feed it all of GitHub.
Yeah.
The brute force approach.
Exactly. The formula has always been more data equals better output.
And to be fair, for the big models that are making all the headlines, it works wonders. But there's a huge catch.
Right, and the catch is what happens when more data just isn't an option? Or, even more to the point, what happens when a language is so complex, so grammatically dense, that you'd need more text than has ever been written in that language to train it?
And that is exactly where you hit a wall. It's a problem we call data sparseness. And it is the central issue in the research we're breaking down today.
We're looking at a paper titled Highly Inflected Language Generation Using Factored Language Models.
It's from Eder Miranda de Noves, Ivandre Peraboni, and Diogo Takaki Ferreira, all from the University of São Paulo.
And I love this paper because it just flips the script. They're not trying to find more data. They're trying to change how the computer actually reads the data it has.
Exactly. They're basically saying that for these complex languages, they focus on Portuguese, but this applies to a lot of them. We have to stop treating words like static images. We need to start treating them like engineered parts.
So let's set the stage. Why does the standard method, the one that works so well for English, just kind of fall apart when you move to a language like Portuguese?
It all comes down to morphology, basically the shape of words. English is what we'd call a morphologically poor language.
That sounds like an insult.
It's not, it's just a label. It just means our words don't change their form very much.
Right, like the verb play. You have I play, you play, they play, maybe played, playing. It's a really short list of forms.
Precisely. The words are like Lego bricks. The brick itself doesn't really change, you just put them in a different order. And because of that, a computer can learn English by just memorizing sequences.
That's the n-gram model, right?
That's the n-gram model. If I say peanut butter and, the computer just calculates the highest probability for the next word being jelly.
Because it's seen that exact phrase, peanut butter and jelly, a billion times.
Correct. But now switch to a highly inflected language, Portuguese. That same verb, let's say speak, isn't just 3 or 4 forms, depending on the subject, the tense, the mood, even the gender.
A single verb can have, what, dozens of different endings?
Dozens and dozens of unique variations. So if a computer is treating every single one of those variations as a completely new, separate word,
the number of possible combinations doesn't just grow, it explodes.
we call it a combinatorial explosion. For a standard model to learn Portuguese, it would need to see every single one of those conjugations in every possible context. You'd need a corpus of text so enormous, it's impossible to build.
And that's data sparseness. It's not that the text isn't out there. It's that the one specific combination you need might only appear once in a million sentences.
So the computer never learns the pattern, it guesses wrong, or just outputs total gibberish.
Okay, so that brings us to their solution, the Factored Language Model, or FLM. How does this tackle that explosion problem?
This is the key insight. They shift the focus from words to factors.
Okay.
In a standard model, the word failed is just a string of letters, F-A-I-L-E-D. But in an FLM, the computer sees failed as a vector.
Yeah.
A bundle of different features.
So it's deconstructing the word, breaking it down into its parts.
Exactly. It still sees the surface word itself, sure, but it also sees the lemma,
The root word, to fail.
the root form fail. It also sees the part of speech tag, so verb, and then it sees the morphological tags, past tense, singular, third person.
That sounds like a small technical change, but I'm guessing it changes the math completely?
Yeah.
Because you're not just counting words anymore.
You're finding patterns in the grammar itself. And the paper gives this perfect example. Imagine a model needs to generate the phrase, he failed. But, and this is key in its entire training data, it has never once seen that specific 2-word sequence.
So for a standard model, it's dead in the water. It sees he, it looks at its database, it finds 0 instances of failed coming next, and it just guesses something common, like he went.
Yep. But the factored model is different. It's never seen he failed, but maybe it has seen he finished a bunch of times.
But finished and failed are totally different words.
On the surface, yes.
Yeah.
But their factors, their grammatical DNA is almost identical.
Both verbs, both past tense, both third person singular.
Exactly. So the FLM generalizes. It basically thinks, Okay, I know that after the word he, it's extremely probable that I'll see a verb in the past tense.
And because failed fits that grammatical profile, the model gives it a high probability even without ever having seen it before.
Precisely. It learns the logic of the grammar, not just the specific phrases. It's a huge leap because it can now correctly predict grammatical structures it has never actually witnessed.
It fills in the gaps from the data sparseness.
It does. And what's great about this paper is they didn't just theorize this. They ran a whole series of experiments on Brazilian Portuguese newspaper articles to prove it works.
Okay, let's get into those experiments. They were testing something called surface realization. What is that?
Surface realization is the final step in generating language. Imagine a system already knows what it wants to say. It has the abstract ideas. Surface realization is the job of turning those ideas into an actual grammatically correct sentence.
So you have the ingredients, now you have to actually bake the cake.
Perfect analogy. And their first challenge for the models was verb phrase lexicalization.
Which is a fancy way of saying picking the right verb.
Right. Specifically picking the right synonym from a list, a synset.
Yeah.
So the concept might be to communicate. But you could use, say, inform, tell, state. The model has to pick the one that fits the context of the sentence best.
How did the standard models do?
Not well. The baseline method, just picking the most common synonym every time, only got about 40% accuracy.
Oof, that's barely better than a coin flip. A news article would be unreadable.
It would. But then they brought in their factored model, one called FLM2. This is a triagram model, so it looked back 2 words, but looked at the word itself plus its lemma.
The root form again?
Yes. And with just that one extra piece of information, the accuracy shot up to around 65%.
That's a really big jump. Why does knowing the root word help so much with picking a synonym?
Because the lemma contains the core meaning. It strips away all the noise of conjugation. To a normal model, spoke and speaking look like totally different tokens.
But the lemma for both is speak.
Right. So the model gets a clearer signal about the topic of the sentence. It understands the underlying concept, which helps it choose the most appropriate synonym for that concept.
That makes sense. Okay, so the second experiment is where I thought the results got really counterintuitive. They moved on to ordering noun modifiers.
Ah, yes. A classic headache in Portuguese. In English, our order is very rigid. We say, the small blue car.
You'd never say the car blew small. It sounds completely broken.
But in Portuguese, it's way more flexible. Adjectives can come before the noun, after the noun. The meaning can even change a little bit, and then you have to deal with prepositional phrases.
Like the end of the corridor.
Exactly. Of the corridor modifies end. The computer can't break that phrase up. It has to know that whole chunk moves together.
So how did the models do on this ordering task?
The standard model got about 65% accuracy, but the factored model, FLM1, hit up to 85%.
Wow. That is a massive improvement. In NLP terms, that's the difference between a system that feels buggy and one that feels fluent.
It really is. But here's the weird part you mentioned. FLM1, the one that did so well, was a bigram model.
It only looked back one word.
One word. The trigram model, which looked back 2 words, actually did worse.
But that goes against the usual AI wisdom, right? More context should always be better. Why did the model with less vision win?
It's a fantastic lesson in signal versus noise. The researchers figured out that for this specific task, placing an adjective next to its noun, the most important information is right next door.
The immediate neighbor.
Exactly.
Yeah.
The question is, does this adjective fit with this noun? When you look back 2 or 3 words with a trigram, you start pulling in information from the previous clause, or maybe the subject of the sentence.
And that just confuses the model.
It dilutes the signal. The very specific local grammar rule was getting drowned out by the noise of the wider sentence. For this one task, it turns out you want a model with tunnel vision.
That's fascinating. So more context isn't always the answer. Sometimes a more focused view is more accurate.
And they took this idea even further with their unconstrained experiment.
The bag of words test.
Yeah. They literally took the words of a sentence, threw them in a virtual bag, shook it up, and dumped them out in a random order.
So blue, car, small, that. Go fix it.
Exactly. Just the raw ingredients, no grammar. And the FLM still did a pretty decent job of reassembling it.
Which hints at something really profound.
It's a hint at the Holy Grail. A system where you don't have to code any grammar rules, you just give it a soup of concepts. And the statistical properties of the factors automatically arrange them into a perfect sentence.
Wow. But we should be realistic. There was a third task where the FLMs I mean, they were better, but they didn't do nearly as well.
Right, task 3. This was the big one. Verb complement agreement in passive voice.
Can you break that down? Give us an example of why it's so hard.
Okay, take a sentence like, the visitors are concerned. In Portuguese, the word for concerned acts like an adjective, so it has to agree in gender and number with visitors.
So if visitors is plural and masculine, concerned has to be plural and masculine.
Correct, and we don't really do that in English. The word concerned stays the same no matter what. In Portuguese, getting it wrong sounds terrible, and they made it harder by putting space between the words. The visitors are not very concerned.
So there's a gap. The model has to hold on to the memory of visitors across that gap to get the ending of concerned right.
That's the long-distance dependency problem. So for this, they built 2 new models, FLM3 and FLM4, that specifically look at gender and number as factors.
They basically gave the model a cheat sheet for agreement.
You'd think that would solve it. And the FLMs did do better than the standard models, about 75% accuracy compared to 68%.
But 75% is way lower than the 85% they got on ordering. What happened?
It comes back to the source data. The researchers pointed out that they were testing the passive voice. And in their training data, those newspaper articles, passive voice was actually pretty rare. Journalists tend to use the active voice.
So even with all the fancy factors, if the grammatical structure itself is rare in the training data, the model still has a hard time learning the pattern.
Exactly. It's a great reminder that these factors are a force multiplier for your data, but they can't create knowledge from nothing. Data sparseness is a stubborn problem.
So let's tie this all together. What are the big picture implications here? Why does this matter for the future of AI?
I think the main takeaway is about efficiency. We live in this era of large language models that cost billions of dollars and need entire server farms to train.
An approach that only works for a few languages, like English, that have a massive amount of text online.
Exactly. It works for English, Spanish, Chinese. But for the thousands of other languages, these highly inflected languages spoken by billions of people, that kind of data volume just doesn't exist.
And this paper shows you don't necessarily need it.
You don't. Novaes, Paraboni, and Ferreira proved that you can get high-quality text generation from a much smaller data set if you're just smarter about how you represent the language.
It's letting us substitute grammatical logic for brute force memorization.
Which means we can build systems that are lighter, faster, and most importantly, accessible to languages that have been left behind by this AI boom. You can build powerful tools for languages like Finnish or Turkish or Swahili without needing a digital library the size of a small country.
So it's about democratizing AI through smarter architecture, not just by throwing more money at the problem.
It's a much more elegant solution.
Before we wrap up, I want to come back to something you said about that bag of words experiment. It feels like there's a deeper, almost philosophical point there.
I think there is. If you can get to a place where the input to a computer needs zero order, just a jumble of concepts, and the output is a perfectly formed sentence.
It changes how we even think about what grammar is.
Right. It suggests that grammar might not be this rigid set of rules we impose on language. It might just be a statistical inevitability, that if you have the right components, the right factors, a coherent structure will just emerge from the chaos on its own.
The machine stops being just a writer and becomes more of an organizer of thought. It takes the messy cloud of human ideas and finds the most probable mathematical path to clear communication.
That's the ultimate goal, a black box where you feed in pure meaning and get out perfect syntax for any language.
So how close are we to language models that don't just write for us but actually assemble thought for us? That's definitely something to chew on.
Indeed.
A huge thank you to the work of Eda Miranda de Neve, Ivandre Paraboni, and Diogo Takaki Ferreira. It's a really dense paper, but the implications are just massive for a truly multilingual AI future.
Absolutely. It was a pleasure to unpack it with you.
That's all for today's deep dive into factored language models. We'll see you next time. Keep learning.